Okay, quiz 5.4, the last quiz before your final. We're doing integrals, definite integrals, and some applications. The region bounded by, okay, so we're just doing regions bounded by curves. We got to get an idea of what it looks like. It doesn't need to be a super accurate graph, but we definitely need to know what's the upper curve and lower curve in relation to them. The boundaries that we're going to use. And this one doesn't really give us boundaries, it gives us three curves. Y is equal to 2x. You have to recognize what type of graph that is. Y is equal to x. And x equals 3, because we are going to sketch the graph of this. Again, this doesn't need to be super accurate. I need to get a feel for where these curves lie in relation to each other. Okay. If you have y's, they're all y is equal to, so they're all convenient. Well, sorry, the last one is x equals 3. Y is equal to makes them convenient because you can just look at the right side and look at the form of it. If you got ax squared plus bx plus c, a quadratic, it's a parabola. You got exponentials, you know what that looks like, logarithms, but this is a linear equation. It is y is equal to mx plus b, and so is the second one. They're both passing through the origin because they both have 0 as their y-intercept. If you think of it in the form of y is equal to mx plus b. This one is slope 2, that one is slope 1. So, 1, 2, 3. Okay, so that line will have slope 2, so it'll go 2 up and 1 over. So it's going to be a steeper line than the other one. Ooh, I need more room. I'm anticipating that I need more room. Nah, that's fine. Okay. Anyway, this one is slope 1, so I'm going to go 1 up and 1 over, so it's going to be a less steep line, but still passing through the origin. Let me draw these in blue. Sorry. I want to label them as well. You don't. All this is just mainly for notes and making sure you guys understand what these look like. Y is equal to 2x. Y is equal to x. And then the third one, so that's not even a region, but it will be a region once we add in the third line. The third line, x equals 3, that's an equation. It's not just a value. In some contexts, you can think of x as equals 3 as a solution, but here it's a curve. It's specified as one of the three curves. So you have to recognize that's a vertical line. Here's 3, and you're looking for all the points that satisfy x equals 3, which are all the points that are in this vertical, or on this vertical line at 3. Okay, and now it encloses it in a region that we now want to find the area of. Okay, so now we're ready to work with this. I'm going to leave space for my next problem. Yeah. I'm just going to do it over here. Okay, so now I can think of it like a region with an upper curve. This is my upper curve, my lower curve, and boundaries. Here's a boundary that wasn't really specified, but it's obvious that these clip off at 0, 0. And then here's my other boundary. So I can think of it as being an integral from 0 to 3. In the region above the y is equal to x, but below the y is equal to 2x. So my upper curve is here, it's going to go first. My lower curve is there. So upper curve minus lower curve. And that's it. That's all I got to integrate. But the setup is the tricky part sometimes, and the graphing helps. Again, it doesn't need to be super accurate, but you do need to get a feel for which one is above the other one. That's going to be a little bit tricky for number 2, but we'll get to that when we get to that. All right, you can do antiderivatives of the terms if you want, or you could, in theory, you could do antiderivatives in theory of each term, but it's better to definitely simplify your integrand when you do something minus something, because a lot of terms will combine. In fact, this one, they do combine, and it's probably easier to just combine them first and then do my antiderivative. 1/2 x squared, plug it in 3 and 0, so it's going to be 9/2, 9/2. Okay, you could, in theory, do geometry. In geometry, that would be your base. You're thinking of it like this. It's sideways, but that's your base. Oops. And your height would be straight up and down from the base. So if we extend it that way, the height would be that. So you got to think of it like sideways. Height going that way. All right, so your height would be 3. Your base would be whatever that difference is for 3. It'd be 6 and 3, so it'd be 3. Half base times height, 9/2. So it is a triangular region, so you could do geometry, but they don't want you to. They want you to get a feel for setting up integrals. You're definitely not going to be able to do geometry for the next one, because the next one is bounded by the curves. Let me write it up. So number 2. I'm going to erase it a little bit because I need a lot of space for this one, but let me get the curves down and start talking about them. This one is y is equal to x squared minus 4x plus 12. That is a parabola, because it's a quadratic equation. The next one, 2 plus 8x minus x squared. I'm going to rearrange them into the usual descending powers, so I can see specifically that my a, my lead coefficient of the squared term, is -1. That's a positive one. So based on the a is equal to 1 there, a is equal to -1 on that one. This one is opening upward, and this one is opening downwards. So presumably, if they're going to bound a region, it's going to be some sort of region looking like that. I'm going to graph it a little more accurately, but that's what we're going to do. And again, they did not give us any boundaries on our own. We will have to figure them out. It'll be based on the intersection of those two parabolas. So, let me think what I'm going to do. This is just a rough sketch. So, I'm looking for the 2 points where they intersect. I don't necessarily need the y coordinates of them. I don't need them as points. I definitely need to know the x values where they intersect there and there. So, I'll be doing that. Let me do it right here. Okay. So we're going to find the intersection. Alright, so it's y is equal to, and when you're trying to find the intersection of two curves that are already solved for y, you're just going to set the equations equal to each other. So that has to equal the other quadratic expression. And then you're solving from there. Maybe the x squares cancels and you get a linear one, but maybe they don't and you get a quadratic. They won't. I'm going to move everything over. I'm going to skip all the steps. That's going to be x squared minus 12x plus 10. Oof. Does it factor? I do have a common factor of 2 I can factor out first. Let me go ahead and do that and see what I'm left with. Is this one of the ones where it factors nicely, or is it one where you're going to expect to be using a quadratic equation? Well, let's try. I think I set this up to solve nicely. I'm not in the mood for a quadratic. So yeah, I did. Okay. I'll double check it always. Negative 5x for my inners, negative x for my outers, and that'll add up to negative 6x in the middle. Negative 5 times negative 1 does give me positive 5, so I'm good. The 2 is part of the factorization, but it's not part of our solutions. We will get two solutions, x equals 1 and x equals 5. Okay, so those are the mean of the bounds of my integral. I could probably work it from there. I can visualize that picture that I drew earlier. It's 1 to 5. So you can just go straight to doing the integration. I do want to review a little bit of, things that you could do to get a slightly more accurate graph, but here my vertex is at negative b over 2a. So it would be, let me see, negative 4 over 2 times 1, which would give me positive 2. So it's going to have a vertex at 2. And when I plug in the 2, I'm going to get 4 minus 8 plus 12. So it would be 8. So the vertex is at 2, 8. And the other one, vertex, the x coordinate will be negative b over 2. I'm just not going to copy down the form, but negative b over 2 again, negative 8 over 2 times negative 1, and that'll be 4. That'll have a vertex at 4. Negative 4 squared, the negative is separate from that because it's part of there. You're squaring this x value. Okay, so it's going to be negative 16, 18. 4 and 18. Okay, none of that's really necessary. Move. Okay, so I've got 1, 5, 4, and 2. Okay, so let me just go 1, 2, 5. I'll go up to 6. Okay. This one's gonna have a vertex at 2, 8, and that was 18. So let me just scale it like 5, 10, 15, 20. Again, this is way more detail than you need. 4, 18. That's the upside down one. So it's gonna go like that. 2, 8. It's going to be the upper facing one, and they will intersect at. Oof. Again, I don't really need it, but I specified I don't need the y coordinates of this. I just need the x coordinates. Yeah, let me find them anyway. What you do is you plug it. You take each one and plug it into either equation, and it should get you the same value. Plug in 1, it'll be 1 minus 4 plus 12 is 9. 1, 9, I believe. I can double check if I plug in 1 into the other one. I mean, negative 1 plus 8 is 7 plus 2, 9. Yep, 1, 9. And the other one, 5. And I'll get my y coordinate by plugging into either equation. 25 minus 20 plus 12 is going to be 17. I can verify it by plugging that 5 into the other equation. Negative 25 plus 40 plus 2. Negative 17 as well. Okay, perfect. Okay, so those are my points of intersection, the actual points, the coordinates. So, let me see. That's a vertex of the downward one. That's another vertex. They'll intersect at 1, 9. And they'll intersect at 5, 17. Okay, so this point, this parabola goes through the vertex and those two intersection points. And then this one, the other parabola, oops, let me move that, will intersect both of those as well. Okay. Yeah. I solved for the vertices of each parabola. I noted that one was opening up and one was opening down, and I got the precise coordinates of my intersection points. All of that being completely unnecessary, but it does, review some of the things that we learned in the past. So I don't consider a waste of time. But if you're working in the quiz, you just need to do this region. The whole question was find the area of that region, and we had enough information a long time ago. I want to go from 1 to 5. Those are my cutoffs for the region. And I want to make sure I do my upper curve minus my lower curve. So my upper curve is the downward parabola, the second one. Minus my lower curve. So upper is the downward parabola. The lower curve is the upward facing parabola. I hope that wasn't confusing. I'm using parentheses around this second one especially because that minus sign between them applies to all of those terms. I don't need that one necessarily, but I'm just going to make sure I group it so you can see the upper curve and the lower curve, and then I'm going to combine like terms. I'm going to erase all this work for vertices and that. And start working this integral. I definitely want to combine like terms because otherwise I could do 6 separate terms, 6 separate power rules, and a lot of fractions. But I'd be better if I could just work with 3 by subtracting, combining like terms. It's going to be 8 plus 4 is plus 12, and then 2 minus 12 is going to be minus 10. Okay, that's simplifying my integral. Now I'm just going to do the power rule very quickly as usual at this stage. Okay, that's my antiderivative. Plug in 1 and 5. Oh lordy. Who came up with this problem? So ugly. plug in the 5 first. Then minus, plug it in the 1 next. Whew. Okay, it's going to be 125. It's going to be 25 times 6. This will be plus 2/3, minus 6, that'll be plus 10. Okay, combine those, I'm going to get negative 248 over 3, and I think, no, I don't think that's going to reduce. No, 3 doesn't go into it. Oof, okay. And then my whole numbers, it's going to be 100. 104. Let me finish it up. I need to calm down there. Again, this part is arithmetic, and just be careful. Okay, so I'm going to have 3 times 104 minus 248. -64. Negative 64. Negative 64? What did I just say? No, positive 64, because that's going to be 300. Okay. And let me mention, if I did have a negative, I either messed up or I misread which one was the upper curve and lower curve. Because if you do switch these, all the terms are just going to be negative, and you'll get the negative of the correct answer. If you do all your computations flawlessly, except you had it set up wrong, where you put the lower curve minus the upper curve accidentally, you just get the negative of the correct answer. But no, I was good. That's the correct answer. Okay. Yeah, so just more, this is a problem I'm going to put in the final, something similar to this, where it's a little bit of graphing, or at least getting a feel for the graphs from chapter 1, doing your antiderivatives from more recent chapters, or this chapter, chapter 5, and then some tedious computations that I'll probably forgive you if you make a mistake there, but set it up correctly and you'll get most of the points for sure. Okay, next page of the quiz. It's a concept that came up in the chapter, but I didn't want to do a whole separate thing, because I wasn't going to really do it for homework. And it's pretty obvious what you're doing. Net excess profit between two separate business plans. One making more profit than the other. It's going to be like this. One's going to have a higher profit, one's going to have a lower profit, and you will be looking at the difference in profit, which is called the excess net profit of one plan over another. So it's going to be something related to this, with some additional questions that came up in this chapter. Average value, and also what's happening to the profit in the long run. That was a limit problem, and we dealt with that a little bit of ways ago. Maybe chapter 4 was it? Chapter 4 covers exponentials. Okay. Alright, the net excess profit of one business plan over another is the difference in profit between the more profitable plan over its alternative. T years from now. Okay, so we got business plan A. T being T years from now. Profit is going to be given by 2 over T plus 1. Okay. Right now, if you plug in 0, you're going to have 2. What is this, millions of dollars, did I say? $1 million, okay. So, as of now, it's making an annual profit of $2 million. This is a annual profit, right? Annual profit of, yep, okay. So it's making $2 million per year as of now. Then what's happening in the long run, we're going to be dealing with that later. You know, but anyway, you look at the limit as t goes to infinity, and it's going to remember the rules. You have a power of t or x on the bottom. We talked about x, but same thing for t. The degree of the bottom is bigger than the top. So this is one where if you put a big number on the bottom, it's going to just be dividing by a bigger and bigger number. So it's going to go to 0. So it's just going to approach 0. So it's going to look something like that. Plan B is given by 3 minus e to the negative 0.5 t. Okay, and then when you plug in 0, I'm kind of jumping ahead and because I do want to see the graphs. But anyway, if you plug in 0, keep in mind e to the 0 is 1. So that's 3 minus 1. So it starts off as 2 as well. It'll start off literally at the same profit. So today, they both have equivalent annual profits. They're both equally profitable. But then you have to see what happens in the long term. That's a question that's going to come up later, but we're going to deal with it now. The limit. And it's a reminder of things in chapter 4, because it's the limit as t goes to infinity of an exponential with a negative exponent. We're using positive t values, it's going into the future, but that negative 0.5 means that that can be thought of as e to the 0.5 t. So I talked about two ways of interpreting it. If you're plugging a very big number into a negative exponent, it gets small. Or if you rewrite it first, you're plugging a big number into a positive exponent, that's going to make the bottom big. But anyway, this term here goes to 0. As t gets very arbitrarily large. So this is approaching 3. And we did deal with some graphs like this in the past. It's going to be approaching 3. Starting off at 2, and then just going a little bit higher. Basically, this term is getting smaller and smaller. So you're starting off subtracting 3 minus 1, then 3 minus 0.5, then 3 minus 0.7. Sorry, let me draw it out what I'm talking about. So this is, again, way more than this is necessary. So at 0, it'd be 3 minus 1. At 1, it'd be 3 minus something that's a little bit smaller than 1. Let me actually do it. Exponential. Oops, wrong one. Exponential to the, what are we doing? 0.5. Negative 0.5. 0.6. Let me do the 2. That's going to be 3 minus exponential to the negative 1. I'll run out to 0.4 because I just want to give you a feel for what's happening. You're doing 3 minus something that gets smaller and smaller, so as you go towards infinity, you eventually get 3 minus 0. So that factor, that term being subtracted gets smaller and smaller, starting at 1 when t is 0, and smaller and it goes to 0. So it starts off at 2 and gets 3 minus 0.6 is 2.4, 2.6. Let me actually write that out one. And eventually just goes to 3. Okay, so 2 gradually approaching 3. That's what it looks like. And so now we're ready to start answering these questions. I'm going to superimpose those two graphs and talk about it. But I actually answered number 5 already, but we'll go over it again when we get to it. Okay, so let's start answering these questions. Total net excess profit. Number 3. And I'll reiterate what the definition is, but let me just profit for both. I'm going to superimpose both graphs. P of A is going down, down, down. So P of A is not good. You're going to be losing money. Well, you won't be losing money, but you'll just be making less and less profit over time. P of B. Plan B looks good. Your profit's growing. It doesn't max out at 3. That's still better than declining to 0. Anyway, the net excess profit is how much more profit. So for a given time, what are we ultimately doing? Over the next 4 years. So let me go ahead and write that in. 1, 2, 3, 4 years. In year 2, Plan B is making that much more than Plan A. That difference is your net excess profit, your net excess annual profit. I want the total net excess profit, so I want the total over the 4 years. So in a certain way, it's just going to be looking at this region. We're going to be accumulating the money that you make over that time span, and we'll see how much more money you make with plan B than plan A. So it's just this integral. 0 to 4. B is bigger. B is your upper curve because that's the more profitable plan. It did take us a little bit of getting a feel for the graph to decide that. And now I'm ready to go. Weird integrals I got to deal with here. B is going to be 3 minus e to the negative 0.5 t. And then P of A is 2 over t plus 1. No like terms I can combine. So I'm just going to have to work with, so I'm going to do antiderivatives here. It does say round, so give an approximation, so this is not going to be a nice exact answer. I mean, we could give it, but it'd be weird looking and hard to interpret for somebody trying to analyze business plans. So we'll get an approximation. Let's see how this goes. Okay. Ooh. I'm going to erase and remind you, I did go through a quiz where I talked about how to do this quickly and what happens with that little coefficient of the variable, and that it's good if you can just do that mentally and not have to use substitution. But, oh shit, I needed that. I'm going to do it again. Let me go through, I'm going to use these two separate pieces. So, e to the negative 0.5 t. Let's just focus on that. It doesn't have a minus in front of it, but I'll ignore that. Okay, let me focus on this because it's going to take use substitution or being really familiar with how use substitution works for a situation where your exponent is a multiple of your variable. So, this is just side work. I'm going to set u to be, again, going back to substitution. You can't really deal with anything other than e to a single variable. That's the only antiderivative that we really know. So I'm going to set u to be negative 0.5 t. Then I have to rewrite dt in terms of du, so I need to take the derivative of this. d is equal to negative 0.5 dt. I usually isolate my dt. Most people do, but there's another way to handle it. It's just moving that constant around, and people move it around and deal with it in slightly different ways sometimes. But this is the usual typical thing. You just get to isolate the dt by itself. Okay, rewriting my integral. It's going to be e to the u. My dt is all of this, so I'm going to have a constant of negative 1 over 0.5 du. I'll pull that constant out. That's just a constant. It's actually negative 2, but if you don't want to work that out, no big deal. You can just leave that as is until we plug it in. So I'll pretend we're just going to not recognize that as 1 over 1/2, which does come out to a nice negative 2 answer, because it won't always be that nice. Antiderivative of e to the u is e to the u. Plus c technically, but we're going to be using a definite integral, so I'm not going to bother with it. Well, let me write it in as a formality. Okay, and then make sure you go back to t, not x, and right here. E is negative 0.5 t with this constant out front. And that's what happens with that constant. So we did do a quiz where I just said, oh, get used to being able to do that, and just knowing it's e to the 3x, and you have to have 1 over that coefficient of that x. Same idea here, ugly decimal, so maybe it's not as intuitive what's happening, but same idea. I just got to have e to that same exponent, and then I got to do 1 divided by that coefficient, which was negative 0.5, so that's where that's coming from. That's like the 1/3 there. Okay, next. And let me start throwing it in. I'm running out of room, and I got to do the other one with substitution as well. So let's see. So I'm going to have 3t, antiderivative of that constant. I do have this negative here, which was not included there, so be careful. It's going to be minus negative 0.5. Okay, and then I got one more more antiderivative to do. So antiderivative of that is 3t minus the antiderivative of e to the negative 0.5t I just did over there. This is showing a lot more detail than I would normally. So again, you know, if you know how things work, so you don't have to write all that out. And then I got to do this one. It's minus, technically. Minus the antiderivative of 2 over t plus 1. I'm going to erase this, make some space, and do again some slide work so I can just focus on that in detail. It's also not that bad, but it is also one that you probably want to do substitution on. Because I have an expression on the bottom that's a function of t, not just t by itself, but it would be convenient to just have that to be a single variable. Because I can definitely do 2 over u. We'll talk about it when we get there, but that's definitely a doable thing because it's just the power of u. So I'm going to set u to be at bottom, t plus 1. The 2 I'm going to pull out anyway, so the 2 is just a constant that I can pull out, which I will. du is equal to dt. And I'm ready to go. 2 comes out. I'm left with 1 over u. And then dt converts to, wait, what did I just write? Sorry. dt converts to du. Sorry, it was a dt originally, and I'm converting it to du. It is a power of u, it's u to the negative 1, but that is a 1 power that does not work with the power rule. That is natural logarithm. I'm going to put back the t plus 1. And that's my antiderivative there. I'm going to write that in here. I have this minus sign here, but it's going to be minus 2 ln t plus 1, and I can omit the plus c. And absolute value is not necessary because we're only going to be using positive t's from 0 to 4, so I'll drop it later. 0 to 4, and I got to plug in, and it's not nice, but we are doing a decimal approximation, and I'll do it here. Oops, minus. These tend to be long, and I'm limited board space, so sorry about that. Alright, these are my antiderivatives with little spaces for me to plug in things. 4 everywhere t is, then 0 in the second one everywhere t is. But be careful. It's a lot of times, especially with polynomials, that 0, if you do have a 0 as your limit of integration, a lot of times it's just 0 cubed, 0 to the 4th, and you just wipe it out at 0. But you do have to be careful with certain trig functions and exponentials and not assume all of this is going to go to 0. Powers of x, yes, but not weird ones like that. Spend some time and just make sure or see what's going on with each of those terms mentally. All right. I got 12. I got e to the negative 2 minus 2 ln of 5. Okay, minus 0 for the 3 times 0. I'm going to distribute that minus sign. It's going to be minus 1 over 0.5. E to the 0 is 1. That does not disappear. That's still going to be a term that we have to deal with. So that's 1. And then minus 2 ln of 1. Okay, so let me see. So 12. I'll do some of my calculator at this stage. And this I just got to type in like that. So these are all going to go into my calculator like that. I can omit that 0. Sometimes we just say that goes to 0. 2 ln of 1 is also 0. Well, ln of 1 is 0, if you recall. Not any logarithm of 1 is 0. This is not 0. This is e to the 0 is 1. So this is a minus that times 1. So that term is still there from that second piece. Alright, I'm ready to type it in now. This is super tedious, but that's what you got to do sometimes. These problems do get tedious. Alright, 12 plus 1 over 0.5 times, you have your exponential function on your calculator presumably. If you're not, you need one that does. I think the iPhone will have it. You just got to flip it sideways. Minus 2 natural logarithm of 5 minus 1 divided by 0.5. Okay, 7.05. What did I say to round to? 1 decimal place. 7.1. Approximately 7.1, and their units were millions of dollars. That is your answer. Okay, so that was the hard part. Well, is it? Number 4. Oh, I might need all this. Let's see. Let me see. What am I doing? Number 4, profit of plan A over the next 4 years. This is total profit. Remember that these functions are annual profit, so total profit will be the accumulation of money over those years. So what are we doing? A. So for what I want to do for number 4, is just take that function there, the annual profit of plan A, and figure out how much money accumulates over the next 4 years, so from 0 to 4. That function was, plan A was which one? 2 over t plus 1. Okay, we're just integrating, and we kind of did it over there, so I wanted to reuse that, but let's see what we're going to reuse. 2 over t plus 1. That's all we're doing, integrating the profit function of just that one plan A, over 0 to 4 years, so 0 to 4. Okay, that's what we're doing. I'm not going to bother doing it. Well, so my antiderivative was 2 ln t plus 1. Not the minus was coming from me subtracting that, but so you can work it out again, but it's going to be 2 ln of t plus 1. I'm evaluating from 0 to 4. Okay, and I'm just doing that. Ln of 1 is 0, so I'm just dealing with 2 ln of 5. That's my exact answer. They want an approximation, I'm assuming. Yeah, we usually want money. That's hard to tell. That's millions of dollars, and who knows what that is until we work it out on a calculator. If I wanted to rewrite that in a different form, or I wanted to match it up with the back of the book's answers, it can be rewritten with that 2 coefficient being put inside. It'd be an exponent, so it's equivalent to ln of 25, 5 squared. So either one of those is an equivalent exact answer. That's one of the situations where I'm just mentioning it in case you work out a problem, they want an exact answer, and you have that, and the back of the book has that. They are equivalent, just using rules for logarithms. I don't want that. I want decimal approximation. So 2 ln of 5 is 3.2. You do ln of 25 as well. It should literally be the same thing. Ln of, what am I doing? 25. 3.2. All right. So $3.2 million is approximately this answer. And then if you did the same thing for plan A and subtracted that minus the total amount for plan A, wait, sorry, what did I just say? This is A. If we did the same thing for plan B, it'd be more money, and we could actually subtract the plan B total accumulation of money minus this, and it would be equivalent to the 7.1 that I had earlier. Okay, but anyway, I didn't make you do that, but you could. Number 5. Oh, thank God. 5 is simple. And we already did it, but I erased it. We'll talk about it again. Long term. Over the long term just means years into the future. decades into the future, centuries into the future, and that means you're just looking at the limit as t goes to infinity. And make sure you look in the right plan. We're doing plan B. Plan B is the exponential one. And I talked about it earlier, but this is obviously going to just be 3 minus something. So basically one thing they can do is they can just apply the limit to that. Limit of a constant is just that constant. And then apply the limit to that, which sometimes you have to spend a little more time on these weird ones. And you have to figure out what's happening with that and know that that's a negative exponent. So as you do a very large negative exponent, it's like e to the negative 1 billion, which is equal to 1 over e to the billion. So the negative exponent means it's a very large thing happening on the bottom, and so this term does go to 0. I did a little table earlier, go back through this video, and where I made a little table showing you what's happening, but this is going from 1 to 0.6 to 0.4 to, and then it goes to 0. So this limit is 0. In the long term, therefore, this plan will be making $3 million, or close to it, per year. That's annual profit over the long term. That's this one over here. It starts off at $2 million per year, and it's getting better and better, but it's kind of maxing out at 3, and in the long term, it'll just stay at steady 3, according to this model, or this graph of the profit. Anyway, that's it. That came from chapter 4 when we dealt with that, and we looked at the limits of these. So go back and look at that, because it's definitely going to be in the final. But anyway, that's the last quiz of the last section that I'm going to have you guys do. So yeah, start studying for your final. I'll have it posted eventually.